All right, in 5.2, we're going to look at the definite integral. Now, the first thing we're going to look at is just the definition of the definite integral, and that comes about from finding the area underneath this curve. Remember, when we did this before, we found the purple area here by adding up the areas of a bunch of rectangles, and we got an approximation. And so that's what this shows right here. The area is approximately this sum. So let's talk about what this sum is. The sigma notation means we're taking the sum of f of x sub I times delta I for each one of these I values. N up here is the number of rectangles. And if you're rusty or if you haven't used sigma notation before, Appendix E is a good thing to look at. I did a short video on that you should look at if you're not familiar with sigma notation. But what this is, it's f of x1 times delta x plus f of x2 times delta x up to f of xn times delta x. N here is the number of rectangles. This right here gives you the height of the rectangles. And this is the width of the rectangles. So for each one of these, delta x would be this width across here. That's delta x, that's delta x, that's delta x, that's delta x. So that's just our width. Now f of xi, basically the xi's inside of here, these are the values that we use to determine the height of the rectangle. If we were using the left endpoints, that would mean we'd use this, 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 and this. So this would be my x1, x2, x3, x4. And of course, when we do f of that, it gives us the height of these rectangles. So for the left endpoint, it would give us this, 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 and this for our four rectangles. If we use the right endpoint, then our xi's would be this, 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 and this. And so our rectangles would look like that, 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 and that. But what this does, the sigma notation lets us write in a compact way the sum of all of those rectangles areas. So, what we saw before was when we have this, if we use more and more rectangles, the limit gets better and better, or the approximation gets better and better. So the idea here is what we're going to do is take the limit of this as the number of rectangles goes to infinity. And we saw that on an example. I want to flip and look at that right quick. We saw this example in the last section where we've got the square root of x and we're going from 0 to 16. If we do this with one rectangle, the approximation is pretty horrible. But if we add more and more rectangles, like if we use 10, we get an approximation. If we use 100, we get a better approximation. And the bigger this goes, the more rectangles we use, the better that approximation gets. So what we do is we think of what happens if we just let the number of rectangles go to infinity. If we do that, then we get the definite integral. So this down here, the area, notice the difference up here. On top, with this sum, with n rectangles, we have a squiggly equal because it's an approximation. But down here, where we have the limit as n goes to infinity, we've got an equal. This is the exact area. Now, you can use this limit. It's possible to take this limit and for a given function, use that to work out exactly what the area is. But it turns out that's kind of It's rather involved. So we're not going to do that. But I do want you to know this is the exact area, and the limit gives the exact area, and this is the definite integral. And this is the notation we have for it. This right here. This thing right here is the integral symbol, and it originated from like an elongated S for sum. But this is read as the integral, or the definite integral of f of x from a to b. And if we look at this, this is the function. We go from a to b, and again, what this really is, it's like we've got the area under here from a to b. It's like we're splitting it up into a bunch of tiny, tiny rectangles. The dx is the tiny width, and f of x is the height. So this integral notation represents like a sum of an infinite number of areas, all of which are essentially zero, but it works out to give us the exact area. So the last thing I want to say in this video is keep in mind the area, this is actually worth writing, area is equal to the integral from a to b of f of x dx. All right, I want to do some examples, but we'll save those for the next video.